Now I have given you about the static indeterminacy, how we have to calculate for beams, trusses and frames. In frames, I have told you the easiest way is the cantilever method. Okay, in trusses, just direct formula. You have total number of unknowns m plus r minus 2j. You will get directly the total number of unknowns which you cannot find from using equations of equilibrium. So, simple cases m plus r minus 2j means we can remember them. Plane structures only we have discussed. Spatial generally not required. In the end, we will see one or two problems how we can manage. Okay. Now, let us see the second topic, that is kinematic indeterminacy. Kinematic indeterminacy or degrees of freedom, dk, both mean the same. Degrees of freedom. Now, what this kinematic indeterminacy or degrees of freedom? I told you at different stages when we were calculating statically indeterminate trusses analysis, when we have taken two topics we have discussed: static indeterminacy, internal indeterminacy, external indeterminacy, like that. Then in the slope deflection method, I gave you about the kinematic indeterminacy, number of independent displacements, number of independent unknown displacements, that we call it as kinematic indeterminacy. Okay, there for a simple beam we have calculated how to find dk. Now here we will see for beams, trusses and frames how we have to calculate the kinematic indeterminacy. Okay, so kinematic indeterminacy means it is the number of independent displacements. It is the number of independent displacements at all joints in a structure. At all joints in a structure. Now, if we say displacement, it can be a linear displacement like a translation, or it can be angular displacement, means rotations. Okay, so displacements include, this is a general term for slopes and deflections. Displacements include slopes and deflections. So here such displacements are counted only at the joints. You will count the displacements, how many independent or unknown displacements are there. Such independent displacements you count only at the joints, not at intermediate locations. Why not at the intermediate locations means, intermediate locations between the supports for a slope or deflection, you have studied in strength of materials about the Macaulay's method of double integration. Entire curve you can define if you know that C1 and C2 constants of integration. So C1, C2 refers to initial slope and initial deflection. If you know C1 and C2, entire deflection curve I can define, slope equation also I can define. Wherever you want I can find slope, provided beginning slope I must know. So that's why displacements are counted only at the joints. Intermediate locations we can get from Macaulay's method of double integration. Then we must know what a joint means. Joint means wherever configuration changes, material changes, cross section changes, we call it as a joint. Okay. Example, supposing that you have, let us say, a cantilever beam. How many joints are there? This point, let us say B, C. Okay, we have a cantilever beam like this. How many joints are there? Number of joints you have to count them as 2, because here this member is connected to the wall. So configuration changed. Here cross sectional area suddenly decreases to 0. Left of C, cross sectional area is A. Right of C, cross sectional area is 0. Because the cross sectional area abruptly changed to 0, it is treated as a joint. Free end is treated as a joint. Why? Because cross sectional area changes from capital A to 0 at C. So cross sectional area changes means that is treated as a joint. Next, second example. Assume that you have a structure like this. How many joints are there? Number of joints, you have to count them as 4. 4 joints are there. 1. See here, up to here it is a straight line. Straight line is meeting a curved member. That means the configuration changed at 2. So wherever configuration changes, it is treated as a joint. Then curve meets straight line. This is third joint. This is fourth joint. It looks as if like this, if you draw only 2 joints are there, but actually 4. Because curve meets a straight line. Here also curve meets a straight line. So it is treated as a joint because curved member meets a straight member. So configuration changed. Configuration changes. Configuration changes at 3, so it is treated as a joint. So finally your conclusion is wherever material changes, cross section changes, configuration changes, it is treated as a joint. Supposing that third example I give you here. This point, let us say A, B, C. This one, cross sectional area same, everything same. It is steel. Assume that this is steel, whose yield stress, let us say 250 MPa. This is also steel, but whose yield stress is say 350 MPa. You can have steel having yield stress 250 MPa, 350 MPa also. It looks as if a single member only, but Fy values are different at B. So material changed. So we have to treat B as a joint. So finally your conclusion is this one. Wherever cross-sectional area changes or material changes or configuration changes, then it is treated as a joint. That means at those joints you have to count how many independent displacements are there. That displacement can be slope or deflection. Only at the fixed beams, supposing Fy are different, at 3 locations only you have to see. Intermediate locations we can define with a curve, with an equation. So they are no longer unknowns. Otherwise, everywhere, if you have a fixed beam like this is there, say, subjected to some load. Here, independent displacement, deflection is different like this. Infinite number of displacements are unknowns only. But entire curve I can define with a single equation. So they are no longer independent. They are all dependent on C1, C2, constants of integration. Okay. So degrees of freedom means number of independent displacements only, we call them as degrees of freedom. So having understood what is the meaning of a joint, how to having understood what's the meaning of a joint, and now at those joints only you have to count how many independent displacements are possible. Okay. Now let us see case 1. We will see how to calculate such dk for beams, trusses and frames. Now first one we will take it. Case 1 for beams. Example 1. Assume that we have a fixed beam. Whatever may be the type of loading, there can be point load, UDL or moments, whatever it is. Only displacements you have to calculate at the supports. Displacement of A, delta A means displacement of A in x direction, 0. Displacement of A in y direction, 0. Theta A is also 0. Here, displacement of B in x direction not possible. Displacement of B in y direction not possible. Slope at B is not possible. So for this case, dk is 0. dk is equal to 0. 0 means there is no kinematic indeterminacy at all. Kinematic indeterminacy 0 means it is a kinematically determinate structure, because all kinematic values we know them. 0 implies that the structure is kinematically determinate. It is called kinematically determinate. What is your conclusion then? Earlier I gave you fixed beams, static indeterminacy is 3 for general loading. Static indeterminacy 3 but kinematically determinate. So that combined conclusion they can ask you like this. Conclusion: fixed beams are statically indeterminate to 3 degrees, but kinematically determinate So comprehensive statements they give you, then we have to take which of the options are correct. Fixed beams are statically determinate but kinematically indeterminate. Second one, fixed beams are statically indeterminate but kinematically determinate. Like that combined statement they give us, then you should be able to answer like this. For that you must know what is ds, what is dk, kinematically determinate. Now second example we will take it. A cantilever beam we take it. This point let us say A, B. At the fixed, this is joint, this is a joint. Independent displacements at all joints have to count. Displacement of A in x direction 0, displacement of A in y direction 0, theta A is 0. Here, displacement of B in x direction will exist. Displacement of B in x direction means what? Elongation. So, this can be possible. Displacement of B in y direction, we call it as deflection. Possible. Theta B, that means slope at B, is also possible. So, if the beams, generally beams means a flexurally loaded member, axial loads either very small value of axial force or sometimes 0 will be there. If you are sure that axial force is 0, then elongation is 0. Then accordingly in the exam they will give you, if you assume that they are the inextensible members or axially rigid members, you will assume inextensible members if there is no load at all, that means they are not elongating. But very small load is there, if you want to neglect the axial deformation, then also we can take it as axially rigid, then deformation is 0. So, two cases are possible in beams and frames, whether they are axially extensible or axially inextensible. Depending on that, two options can be given. Any member if axially rigid does not mean that flexurally rigid also. They have to specify. Flexurally rigid means EI is infinity. Axially rigid means AE is infinity. Whatever they ask you to take it as infinity, only that we have to take, other we should not take. That is possible to happen, we should assume. Okay. So, such cases, now you see dk when extensible. Two cases we have to see. When extensible means members are capable of extending 3 degrees. What are they? Delta Bx, delta By, theta B. Okay. Now dk when inextensible. Dk when inextensible. Inextensible means they don't elongate at all. That means they are axially rigid. Inextensible, axially rigid, both mean the same. Or axially rigid means 2 degrees. What are they? Delta By, theta B. That's all. Delta Bx, which is elongation, is not possible. If you assume that they are axially rigid, it means that elongation is not possible. So, delta Bx we take it as 0. Then accordingly you have to take it as 2 degrees. Okay. So, that's how we have to make it. So, general thing we can write it. Dk when inextensible. You can write it like this: dk when extensible, general case, minus number of independent displacements prevented because of the axially rigid nature, that you subtract, minus number of independent displacements prevented. Number of independent displacements prevented due to inextensible nature. Okay, that thing not required. Independent displacements prevented, we can write it. So, how many independent displacements are prevented? Only one. 1 is 0. That 1 is delta Bx is 0. So decay when extensible is 3 minus 1. So you get 2 degrees. This is the most general expression. First, in the exam also, if they don't mention anything, first you will take extensible case. That means general case they can extend. So 3 degrees is the answer. First search for 3. If 3 is not there, then search for 2. Only then you have to search for 2. Means axially rigid they might have assumed. Then accordingly independent displacements you subtract, check the result, which anyone must tally. 3 and 2 both they will not give. If nothing is mentioned means both they will not give. If nothing is mentioned, 3 degrees you have to answer, because you have to take it as a most general case. Okay, so I give you that note. Always you remember this one. If nothing is mentioned, in the problem, assume that all members are extensible and find decay. First you have to assume that they are extensible, find decay. In case no option is matching, then subtract one more. Inextensible you take it, then check the result. So that is the process. Now let us see how we have to calculate in the exam. Now find decay. Supposing that you have like this A, B, C, D, E. Simply they said find decay. Whether members are extensible or inextensible, we don't know. So you will proceed this way. First one, displacement of A in x direction 0, y direction 0, theta A is 0. Nothing is mentioned, so they can extend. AB member can elongate. To facilitate that elongation, this rollers roll. If it is strength of material, sir might have told you, simply supported beam, if it is subjected to temperature changes, the roller support move to facilitate the free expansion or contraction, so that no stresses will develop in simply supported beams. That is the case here. So displacement of B in x direction, then y direction is 0, but theta B can exist. So at B, displacement of B in x direction, theta B possible. Here delta Cx, theta C are possible. Here delta dx, then theta d are possible. Here displacement of in x direction means elongation, deflection, slope. 3 are possible at E. If delta Bx is 5 mm, Cx need not be 5 mm, because in strength of materials you have studied, supposing that a bar of length 3 meters, subjected to axial force of 10 kilonewton, 20 kilonewton, 30 left side, 40 right side, like that were there, then total elongation, if you, when you are calculating, delta L1 plus delta L2 plus delta L3 calculated. That means delta L1, delta L2 are independently you calculated, P1 L1 by A1 E1, P2 L2 by A2 E2. So independently you calculated the elongations. That means independent of the other member, this can elongate or contract. So that's why all of them are independent elongations or independent contractions. So first case is this one, dk when extensible. First you calculate dk when extensible, 2, 4, 6 plus 3, 9. 9 degrees. 2 plus 2, 4 plus 2, 6 plus 3, 9. Supposing that in the options 9 is not there, then you will calculate by spending another 10-15 seconds extra. Dk when inextensible. Dk when extensible minus number of independent displacements prevented. If at all they are inextensible, suppose 2 meters are there, axially rigid, B will not elongate at all, no contraction at all. So elongation or contraction is called first order displacement, PL by AE. Now when load is applied here, it will sag. When it sags, then B slightly inward movement will be there. This is what I have told you. Supposing that you have a simply supported beam A, B. Okay. Now if you apply P here, delta Bx is PL by AE. This is called first order displacement. Supposing that if at all apply load P here, say A, B, no axial force, so delta Bx now in this case is actually 0, but when it sags, this is what you have studied in strength of materials also, when load is applied like this, it will deflect like this. See here, this curved length is more than the straight length, like this will be there. Load when you apply, it will sag, means it has to come inward. That inward displacement, because of this vertical displacement, is called second order displacement. This is delta B dash due to downward displacement. This point, let us say C, C comes to C dash due to downward displacement of C is called second order displacement. It is taken as 0 because supposing that this is some theta b, yb into theta b, the inward displacement when you want to calculate, what happens is that inward displacement is a function of the theta and also the deflection. If you multiply, if you take that circular arc, you will know how much inward movement it will go. Then that will be a function of this y and also the angle subtended at the center, theta into some y, you will get it. So small, theta itself is very small, the curvature that it makes or slope it makes at the topmost point, very small, multiplied by the deflection is also very small quantity. Two small quantities when you are multiplying, the value is so less. So is the case, we take it everywhere, whether you take structural analysis or in the plastic analysis, wherever you are getting displacement in terms of theta into some y. Theta is very small, y is also very small, so theta into y means you can neglect. If at all you multiply to get a displacement, if you have to multiply two displacements, that means displacement square you get, say, that is called second order displacement. Second order displacement means displacement has power 2. We will neglect because displacement itself is very small. Supposing that this what you have learned, if y is say 0.001 mm, y square will become second order displacement. How many zeros you have to write? Like this. This is second order displacement. Second order means y has power 2. If displacement has power 2, we have to neglect. So here also in kinematic indeterminacy means we don't count the second order displacements. Okay. So taken as 0. So delta Bx in this case 0. We have to take it as 0. So you should not get a doubt here that when you apply load here it will sag. So B will come in. That is not a displacement. If axial pull is there, if it elongates, then only the displacement is counted. In the plastic analysis also I will discuss about these second order displacements. So that why we are neglecting the small values, we will see that in that point. Okay. Now, so this point is clear. Number of independent displacements prevented now are 1, 2, 3, 4. In this particular case, delta Bx, delta Cx, delta Dx, delta Ex, all of them are 0. So dk when extensible is 9 degrees. Because you assume that they are inextensible, 4 displacements become 0. So you will get 5 degrees. So first search for 9, this one. If 9 is not there in any option, check for 5. Then 5 will be there. That means you might have thought that it is an actually inextensible case. Okay. Now we'll take one more example. We'll take now one more example. Find dk. In this example, at E what we do is we will fix here. This is a fixed support. Now you see, in this case, whether extensible or inextensible, displacement of E in x direction 0, Ex 0, Ey 0, theta E 0. So that is a compatibility condition. Deformation tells you that elongation has to be 0 because you fixed it. It is independent whether the members are extensible or inextensible. Now when dk when extensible means how to count? 2 edges are 0, 0, all zeros. Here 2, 4, 6. So only 6 degrees you will get in this case. So when extensible case it is 6 degrees. This is delta Bx, theta B, delta Cx, theta C, delta Dx, theta D. Only 6. If both ends are fixed, how this joint can elongate? Can elongate because supposing that AB member elongates by 5 mm. So delta Bx is plus 5. In the inextensible case, delta Bx is plus 5. 5 mm it elongated. Assume that delta Cx elongated plus 3 mm. Now delta Dx also elongated. How much is that? Say 2 mm it elongated, say. Elongation, elongation, elongation. Then this member might have contracted by how much amount? 5 plus 3 plus 8 plus 2, 10 mm. So this member is not independent. This member must contract by an amount of 10 mm. So actually this is like this, delta Ex is 5 plus 3, 8 plus 2 minus 10 means it has to be minus 10 mm, not unknown. That means DE member minus 10 mm, this is plus 2 mm, plus 3 mm, plus 5 mm. 5 mm elongation, 3 mm elongation, 2 mm elongation. So 10 mm, 3 members elongated. This is not unknown. Not unknown means it is not independent displacement, it is a fixed quantity, it has to be minus 10 only. So that's why independent displacements means Bx, Cx, Bx, Cx, Dx only. Ex we will take it as 0 itself. That means accordingly delta, the contraction in the member dE, in the calculations it will come as minus 10 only. Okay. So like that independent displacements prevented are now how many are prevented? In this case only 3. What are they? Delta Bx, this is when the members are elongating, the 6 degrees I have explained, Bx, Cx, Dx all are possible, so 6 degrees. Now if the members are inextensible, even Bx, Cx, Dx, that 5 individually also this will become 0. So delta Bx, delta Cx, delta Dx, now they will become 0. Delta Ex already 0, again because of inextensible nature again it will not become 0, already 0 only. Because when you are subtracting independent displacements prevented, how many extra displacements are becoming 0 because of your inextensible nature? If it is already existing 0 is there, say, that is not because of inextensible nature, because of fixed support already it is 0. But if you assume that the members are inextensible, additionally only these 3 will become 0. That's all. That's how we have to see. So now it will become 6 minus 3. 3 degrees you will get. This problem also, when both ends are fixed, 3 supports are there. First you have to search for 6. Dk when they give 6, 4, 3 will not be there. 6, 4, 2, 1 they give you, say, then 6 you will answer. Then if they give you 4, 3, 2, 1, then 3 you have to answer. This is like this. Nothing is mentioned. Option A is 6, 5, 4, 2. Then 6 you have to answer. Supposing that like this they don't give. Option A, 5, 4, 3, 2. Then 3 you will answer. If they give like this 6, 5, 4, 2, it means that he is expecting you to calculate for a general case. Then accordingly 6 will come. If you see this one, then you have 10 seconds extra time. First dk when extensible you calculate, 6 you are getting, but 6 is not there. Then you check when inextensible case, 6 minus 3, 3 is there. Then 3 you check it, then 3 you have to answer. These options will decide most of the cases whether he wanted us to give them in the form of extensible case or inextensible case. But sometimes they clearly mention if the all members are axially rigid, then dk is, then you have no choice, they have give you this only. I think you understood all the ways of asking the questions. So we have seen dk for the beams, how we have to calculate. If they don't mention anything in case of beams, we must assume that the members are extensible. So general case you have to calculate dk. Then if nothing is mentioned also, first we calculate general thing, that means extensible case we take it and find dk and check the result. If no result tallies, then you have to take the members are inextensible, find dk, then check the result. So this is the sequence I told you, this is what you have to take it. You will have 2 minutes time, maximum of 20 or 30 seconds time, you can complete the problem. Now we'll see the second case, how to find dk for trusses. Kinematic indeterminacy for trusses. Example. Assume that we have a truss like this. Simple truss we are taking. Is a hinge support. Here it is a roller support. And assume that you have applied some load W. This point let us say A, B, C. And when you increase the loading, assume that AB member buckled and rotated by say theta. This is say theta 1, theta 2. This type of rotations we will not consider in trusses, because as I told you, in trusses all members are links, means only axially loaded members. If any axially loaded member bends, it is not called bending, it is called buckling. This type of unwanted bending is called buckling. If any member under compression buckles, then it means that the member failed. It means that the structure failed. For a collapsed structures, we don't find decay. Supposing that we have built one structure, a 10-storied building, assume that due to some loading, the structure collapsed. Then you don't lift the bricks and find decay is 36, 47, no meaning once it collapsed. Here also meaning is same. If a structure collapses, finding decay means absolutely no meaning. So we will not consider these rotations theta 1, theta 2. These are the rotations after deformation. That means rotations after buckling. We will not consider. So this means that member buckled. It means that structure failed. Then for collapsed structures, we don't find decay. So rotation after deformation. That is buckling rotations. Are not considered in trusses. This is the first thing. Now let us see the second example. Second example is this one. Assume that we have a truss like this. This point let us say A, C, B. You have applied some loading and naturally it will deform. Assume that it has come to this position like this. Zoomed view I have shown, but okay, no problem. After loads are applied, C has come to C dash, B has come to B dash. In the process, from here to here, this is the displacement of B in the vertical direction, displacement of B in Y direction, and this is displacement of B in x direction, delta Bx, delta By. Now, this is the rotation. See, the member AB did not bend but rotated. Without bending, if it rotates, we call it as rigid body rotation. That means without developing any bending stress, if it rotates, we call it as rigid body rotation. Okay. So, this is rigid body rotation. Also, we will not count because of this reason. If you know delta Bx, delta By, it means that Bb dash is known to us. If Bb dash is known to us, I can find theta. How? If Bb dash is known, we can find theta. How that is? L theta is equal to Bb dash. So, theta is equal to Bb dash by L. So, not unknown. So, this is not unknown. Theta is not unknown. If I know delta Bx, delta By, theta B, we can find just by simple geometry. The degrees of freedom or number of independent displacements means they should be independent. Means without knowing them, you cannot proceed further. If I know these things, if I can find, that means theta is not independent, it is dependent on delta Bx, delta By. So, this type of rigid body rotations also we will not consider in trusses. Rigid body rotation are also not considered in trusses. Why? Because they are not unknowns. That means in the trusses, either rigid body rotation or rotations due to buckling we will not consider. Only translatory displacements only we will consider in the trusses. At each joint, two possible displacements, that two linear displacements are possible. Rotations we will not consider. Okay. So, that is your final conclusion. Due to different reasons, we will not consider rotations. One rotation we will not consider because it means structure failed. Another rotation we will not consider because it is not unknown. Okay. So, now you write the conclusion. At each joint in a truss, number of independent displacements are only two. What are they? Delta x, delta y. Rotation of a member in a truss is not considered because it implies that the member buckled. So, for a collapsed structure, we don't find decay. Next, rigid body rotation. Rigid body rotations are also not considered because they are not independent displacements. That is, they are not unknowns. They are not unknown displacements. Second point is, in beams, I have told you two cases. You can consider member as axially rigid or axially extensible. Two possibilities, because there may be a possibility that in beams compressive force may be there or tensile force may be there or it will bend. Okay, but primary force in beams is bending, secondary force is axial force. Sometimes it will be zero, sometimes it may be existing, but very little value it has. So you have a choice of selecting members as axially rigid or extensible case. But in trusses that possibility is not there, because in the trusses primary force itself is axial force. That means axial contraction or elongation is a primary deformation. That you cannot take it as zero. So here only one case. Members are extensible case only we can take it. Members are axially rigid, you cannot take it because forces you cannot neglect. Considerably large amount of axial forces only will exist. So the question of axially rigid case in trusses will not exist. Okay, in trusses, we cannot assume that members are inextensible, because primary force is axial force only. Primary force is axial force only. This is like assertion and reasoning type also they can ask. See, once you read the notebook thoroughly, first to last, completely you should understand them. The meaning of this primary force, axial force only means you have to understand that. Why you cannot take axially rigid, you should have clear picture. Only then any type of question, assertion and reasoning type or multiple choice questions or multiple select questions, anything you will be able to answer if you read the notes thoroughly. Okay. Next, let us see how we have to find dk. Now let us see the numericals. dk. ABC. Now, at a hinge support, it is a truss, no rotations. So theta 1, theta 2 not possible. Now, even xy displacements, translations are also not possible at A because of the pin. Pin cannot move because it is connected to a hinge support, means it is connected to the ground with the help of two triangular plates. Front and back triangular plates will be there. That means here dk is 0 at A. At A dk is 0. But at this point dk is 2. What is that 2? Displacement of B in x direction it can move. Displacement of B in y direction. If it comes here, say delta Bx, delta By, because loads are applied. C can only move up to here, as we have seen. So at this point delta K is 1. What is that 1? Delta Cx. Delta Cy is not possible because there is a roller. Roller will not permit the upward and downward displacement. You should not assume that roller together it will be lifted up. In any case, whether it is a guided roller support or this type of roller support, there will be on this rigid plate there is a channel. So it will hold it. In a guided roller support, it simply translates, but in this case it will rotate also because of the bolt. If it is rigidly connected, it will not rotate, it will only translate. There is only difference between the guided roller support and roller support. It will rotate here because arrangement is different, connection details are different. So dk is 1. So 0, 2 plus 1. So dk is 3. 2 minutes time. You can complete, instead of 3 joints they give you 5, 6 joints. So on the supports and intermediate locations just put them 0, 2, 1, 3 like that. 0, 1, 2, that's all. So finally you can count it. You don't have to use any textbook formula to find dk of a truss. Suppose 7 joints are given, say. If they are floating, that means they can translate, then 2, 2, 2 you assign, hinge support 0, roller 1, that's all. Then add it. 20 seconds you complete, whatever 1.5 minutes if you get time, you use it for some other purpose. You should not think that how such a simple question can be given in the exam. Let me think difficult way to get the solution should not be there. Okay. Supposing that if you have say like this. Say this way. Rotations we don't permit, they are not, means rigid body rotation or rotation after deformation are not there. So just count here, here dk is 0 because it is a hinge support, here dk is 2. Whether counter bracing is there or not, they may reduce the deformation, means translation and or reduce the deflections, but they do exist. You can neglect only second order displacements, means delta power square or theta power square, wherever you find in your expressions, they are called second order displacements. Displacement of order 2 means y square or theta square terms we can neglect, but single displacements, first order displacements, however small it may be, you cannot neglect. So dk2, so here also dk2, 2, here dk is 1, it can only move, here also dk is 1, it cannot move horizontally, vertically. So 2, 4, 6, 7, 8. So kinematic indeterminacy is 8 degrees, like that. Okay. So this is the point. At hinge support in a truss, horizontal and vertical displacements are also not possible because pin is held by two triangular plates Pin is held in position. Held in position by two triangular plates. That means I told you first triangular plate, front side one, back side one. Embedded inside is there is a bolt, and that bolt cannot move even x or y directions also. That's the reason you cannot make it. Next, this is about the trusses, simple case. Now let us see for the frames, how to calculate frames. Case 3. DK for frames. Now, in the frames, this was the point. In the frames, beams and columns, you apply a transverse loading also. Link behavior will not exist in the frames. If at all it exists in any particular member, again only axial force will be there. But otherwise, in the frames, if any member rotates, that is not called buckling. Because of the transverse loads, if they bend and rotate, it is rotation only. Bending, rotation. Okay. So you have to count rotations in the frames. If you have a rigid joint, 10 members are meeting at one joint, say, if moment is applied, all members rotate by the same angle. So at a rigid joint, only one rotation you have to consider. XY displacements plus only one rotation. If we have a pin joint, 10 members are connected, let us say. But it is not a truss, it is a frame. Suppose in a frame you have a pin joint and connected 10 members. Then 10 members rotate independently. They are not buckling rotations, they are bending deformations only. So 10 rotations you have to count, and x and y translation and translatory displacements also you have to consider. Okay. If any member is axially rigid, if they mention, for that member in the longitudinal direction, deformation is not possible. If 10 axially rigid members are there, if they mention, so 10 you have to subtract, because 10 axial deformations in the direction of the longitudinal axis not possible. So with these 3 points, we can find decay of the frames also in 20 or 30 seconds time. Okay, let us see what those points are. At a rigid joint in a plane frame, all members rotate by the same angle. So we have to count only one rotation. One rotation for all members meeting at a rigid joint. Count only one rotation for all members meeting at a rigid joint. So this is the point you have to remember. Next, second point is, at a pin joint in a frame, all members rotate independently. So we have to count rotations of all members rotations of all members meeting at a pin joint. At a pin joint, each one can rotate independent of the other member. Next. So, we have to count all members rotate independently. Count rotations of all members meeting at a pin joint. Next, third point. If members are inextensible, extensible and inextensible opposite words. Inextensible, or if they give axially rigid, both mean the same. Inextensible or axially rigid, then deformation of each member in its longitudinal direction. Is not possible. Okay, with this understanding, now we will try to find the decay for the frames. These are the three considerations. Find decay. Assume that we have a plane portal frame, say like this. This point say A, B, C, D. Because it is a rigid joint, B, see at beam level there is no support here, so it can sway. That sway can be to the right or to the left depending on the horizontal force direction. Assume that it sways to the right, okay, and AB member axial force also is there, so it contracts, sways. So B has come to say somewhere here B dash, okay. Initial direction is this one. These are initial position, so it has come to say B dash. Now it rotates. Rigid joints rotate after bending. So the deflected shape of the beam, assume that it has rotated by some angle. Like this it goes up, somewhere here it stays, entire deflection profile. Right now we are not interested. You see this is sagging. If you drop a tangent from the initial line, this is clockwise rotation, this is a theta B, and deflection profile is sagging. If it sags when there is no external movement at a joint, if one member sags, another member also must sag, otherwise that 90-degree angle you cannot maintain. So here it should sag, and the deflection profile will go something like this. Like this. Okay, it has to sag only. This rotation, if you drop a tangent to this curve, like this it will go. So sag, this is also sag. This angle has to be theta B only. If this is theta B, it has to be theta B. 90-degree angle should be maintained. So angle between the tangents, red color dotted line, blue color dotted lines, 90 degrees only, they are separated apart. Okay. So you will find that at a rigid joint in a plane frame, three displacements are possible. One is translation, from here to here, you can call it as delta Bx. This way, this displacement we call it as sway. From here to here, B to B dash, this is delta By and theta B. So here 3, same here delta Cx, delta Cy, theta C. So like that 3 displacements are possible. So you can write dk when extensible, when members are extensible, is 6 degrees. What are they? Delta Bx, delta By, theta B, delta Cx, delta Cy, theta C. This delta Bx generally we call it as sway. Now delta Bx, delta Cx, they will not be same. If delta B frame as a rigid body, it sways by 10 mm say. BC member, there was a tensile force, let us assume. So tensile force, it forced it to elongate by 5 mm. So 10 rigid body translation, so this will go 10 plus elongation of this member 5 mm. 15 mm will be there. That means delta Bx, delta Cx are not equal if the members are extensible. So because BC member extends by 5 mm, let us say. So sway plus 5 mm is the total displacement of the joint C. Like that. So that's why 6 degrees. dk when inextensible. How will you find? General case, dk when extensible minus number of independent displacements. Number of independent displacements prevented. Now I told you independent displacements prevented means each member in its longitudinal direction deformations are not possible. So there are 3 members. So 3 deformations are not possible. So independent displacements prevented are 3. Now general case if I take it, dk when extensible is 6 minus 3, you will get 3 degrees. dk is general, this is 6 degrees, 3 degrees. In the exam again, if they don't mention whether they are axially rigid or not, they mentioned nothing, then first search for 6. First calculate general case 6 degrees. If one of the option tallies 6, you put it. If 6 option is not there, then search for 3. That means he considered maybe all are axially rigid and gives you. Sometimes to avoid the trouble, they will mention in the beginning itself all members are axially rigid, find dk. Then no chance. Then this is also will find. Then also will find this minus independent displacements prevented. It gives us easy way of getting out of the problem. Okay. So what are your conclusions? Is this one. At a rigid joint, in a plane frame, number of possible displacements are 3. Okay. Space means space joint is there, say number of possible displacements will become 6. Now what are in this case number of independent displacements are prevented? What are those things prevented? AB member in its longitudinal direction displacement is prevented. That means what is prevented for AB member is delta By 0. So in this case delta By 0. For this member what is prevented? If it sways by 10 mm, B sways by 10 mm and C also will move by 10 mm only because that elongation is 0. That means delta Cx will be there, but it is not independent. It is known to us, means it is equal to delta Bx only. Delta By 0, delta Cx is not unknown. Why? Delta Cx is nothing but delta Bx only. This is the second one. For the third member, what is not unknown is, what is known is CD member cannot contract. So displacement of C in y direction not possible. That means delta Cy is 0. So delta By 0, delta Cy 0. That means if the members are axially rigid, some of the displacements will be 0, some of the displacements are not unknowns, they are known quantities. Like that it will happen in the process. 3 are known displacements, means either 0 or we know its value. So 6 minus 3, 3 degrees. So at a rigid joint in a plane frame, number of possible displacements are 3. Second point is this one. How those 3 things we have to make it. If the members are axially rigid, then deformation of each member in its longitudinal direction is not possible. So for AB member, what is not possible? For AB, delta By is equal to 0. For AC, no, BC. For BC member, delta Cx is not unknown. That means delta Cx is nothing but delta Bx. Then for CD member, what is known? Delta Cy is 0. Like that, for each member, deformation in its longitudinal direction not possible means either it will be 0 or it is a known quantity. Okay, so that's what you have to take. Axially rigid may be given or axially extensible case. Now, let us add bracing. Bracing rods, they are not part of the structure, we should count. If they give them as bracing rods means length of a rod say 5 meters. Under compression, the rod becomes, or rod buckles, very little amount of compressive force only it can take. So we assume that the compressive force in the bracing rod, it is such that it is ineffective. Only one bracing rod which is under tension, that will only resist the sway of the frame. Let us see the same problem. If bracing is done, how we should manage? Till now that question is not given. So in case this year gives, if they give us a new question, means this is the only new question they can ask. Find decay. This is actually our frame. This is bracing rod. In the exam, different colors they will not give. I am telling you that this is a not part of this structure. Only purpose is to reduce the sway. Okay, like this. They are straight members. Like this, they are interconnected. These are bracing rods. Used to reduce sway of frames. Okay. Now let us see A, B, C, D. Now DK when extensible, that means when members are extensible, again same 6 degrees, delta Bx, delta By, all are possible, theta B, delta Cx, delta Cy, theta C. But if the members are inextensible, that means the rod is also inextensible, it will not permit the frame to sway to the right side. So dk when inextensible, general case dk when extensible minus number of independent displacements prevented. Now independent displacements prevented in this case will become 4, because delta Bx is 0, delta Bx 0 means delta Cx 0, or delta Bx is equal to delta Cx is equal to delta By is equal to delta Cy. All of them will become 0. That means if bracing rods are there and members are inextensible, only rotations are possible but not the displacements. So you will get dk when extensible, when inextensible. Extensible case is 6, displacements prevented are 4, 2 degrees you will get. What are those 3 degrees? Theta B, theta C. Without elongating the member, they can rotate. Then you will get a doubt that how they can rotate, elongate, that means length will increase when they are rotating. So that means they have to displace, but they are second order displacements. See, what it means is, note, supposing that you have a member like this, load W, length is L, this point say A, B. If it bends, it will bend like this. What you assumed, that the displacement is vertical. This curved length, it looks as if it is longer than the straight line. That means elongation is there, but elongations are neglected. Actually what happens in this case, B will come to say B1. This you have taken delta By. Axial force is not there, let us say. You see slightly it went inside, length is same only, black color length, blue color length same, but it is a curve. That means it must have gone inside, like this. This point B2 say. Strength of material salt told you BB2 is delta By. Then slope, drop a tangent, theta B calculated. But inward displacement B1, B2 he didn't write it. This is B1, B2 is second order displacement. Last class also I told you such type of second order displacements. Why it is second order displacement? If I take this as a straight line, if I take it as a straight line, if I want this one, this is delta by, this is theta b, some theta you take it. So b1, b2 is delta by, itself is very small quantity, 0.001 mm like that. Then theta is 0.001 radian. If a small displacement is multiplied by another small displacement, then it is called second order displacement. You round them off to 0. In SM you have done that inward displacement you didn't calculate. So is the case here. If at all a straight member was there, if it rotates, it looks as if length is more, but that to accommodate that increased length, the BC values they will go in. But that inward displacement is so small, like that is like a second order displacement. So we will not count we take that second order displacement as 0. So we will take now only rotations are possible. Rotations are theta b means if it rotates theta b like this, it goes up like this, say. BC is the black color, theta b, theta c, somehow it rotated, let us assume. Like this it rotated, say. Red color dotted line is longer than the black color line. How is it possible? That means it might have moved outward or inward depending on the displacements. That means B and C also sway, means they move. We should not think that way because of that reason. It is a second order displacement. So round them off to 0. That means even if the members are axially rigid, they can rotate without elongating. So 2 degrees are possible. Let us take this as one conclusion. That means in the exam, to increase the speed, this is our overall observation. If members are axially rigid, and bracing is done, then only rotations are possible. Then only rotations are possible. Sway is also not possible. Not possible due to bracing rods. Now you see, one diagonal will be under tension, one diagonal will be under compression. Now if the frame sways to the right side, which diagonal is under tension, which diagonal is under compression? See here, this is the, in strength of materials you have studied like this. A small element in a truss you have taken, due to shear deformation, if it goes like this, say, clockwise, anti-clockwise, like this shear Q has given, and it deforms. How it deforms? It goes like this, say. This is a deformation. Sir told you, if at all an element is subjected to pure shear, one diagonal is under compression, one diagonal is under tension. They are called diagonal tensile stress and diagonal compressive stress. Now come to this one. Initially this is the diagonal. For the black color one, this is the diagonal. After deformation, after it sways to the right side, this length became like this. See, compared to the top dotted line, bottom red color dotted line is longer. That means someone might have pulled that. Otherwise, why unnecessarily it will elongate? That means this diagonal is under tension. Now you visualize this as a portal frame. If it sways to the right side, this diagonal is under tension. The other diagonal initially which was here, up to here was the initial length. Finally what happened? This much it became. You see, compared to this dotted line, this is so small. That means this diagonal got contracted. Why it will contract? Sir might have told you it is subjected to compression called diagonal compression. So in this case, if the frame sways to the right side, this diagonal will be under tension. Because they are not axially rigid, it will elongate and permits the sway also to happen, but magnitude of sway will be less. They will reduce the sway, but it will not make them zero. But if you treat them as axially rigid, if sways to the right side, say this will elongate, this will be under tension, but no deformation is there. That means without elongating this member, C cannot go right side. So that's how the sway is not possible if it is axially rigid. So then this diagonal is under compression. Under compression, being a small rod, we assume that it buckles and it is ineffective. If it is ineffective, why should we provide? Then it is not necessary that it should sway right side only. If it sways to the left side, then this is under tension. So this will be effective, this will be useless. In the frames, we don't know in which direction they will sway. Two directions they will sway. That's why two bracing rods. You design bracing rods always for tension only. Compression, we assume that they are ineffective. Okay. Now let us see. I think about the second order displacements for this type of curve. To accommodate that one, BC they have to go in or out, but they are so small, as I have explained. Delta By into theta type displacements, they are round them off to 0. Now we will take a similar example, dk. This one is also like a bracing, A, B, C, D, E. All A, E, D, C are fixed, B is a rigid joint and loading is done, say. Such cases, dk when extensible, 3 degrees are possible. What are they? Delta Bx. Delta Bx, it can move right side, it can move down also. For B to move down, both must be under compression. So they are contracted and somehow it comes to here, say, depending on the final position, one may be tension, one may be compression. So like the delta Bx, delta By, theta B. There are around 4 members are there. dk when inextensible, dk when extensible minus number of independent displacements prevented. How many displacements are prevented? Because of this axial rigid nature, Already only 3 are there. How many you can prevent? 10 you cannot prevent. 1, 2, 3, 4 members are there. 4 axially rigid deformations are prevented. But 4 decay itself is not there. They are all interconnected. That means the deformations of these 4 deformations are not independent. From the geometry, we can get a relationship between the deformations from the compatibility conditions. So, possible displacements are only 2. Out of that, how many you can prevent? Only 2 you can prevent. 3 possible displacements, 2 you can prevent. What you can prevent is delta Bx, delta By. So, 3 minus 2, only 1 degree. What is that 1 degree? Theta B. Like that. Though there are 4 axially rigid members or 4 members are there, the 4 deformations are not independent. When they are interrelated, 4 axially rigid members you cannot stop. 4 axially, earlier 3 members are there or 1 member means 1 you have subtracted. If 2 members are there, 3 members are there, 3 you subtracted. Here 4 members are there, 4 you cannot subtract because the displacements that happen because of the nature of the structure, they are not independent. Even the linear displacements are not independent. Only out of 4 members, displacements are delta Bx, delta By. If I know delta Bx, delta By, other deformations you can find. They are not independent. So, accordingly you subtracted only 2. So, 1 degree. Now, let us see in one of the GATE papers, they asked a question like this. Considering the beam as axially rigid, the degrees of freedom for the plane frame shown in figure is, this is a problem. There is a roller support, hinge support. That's all. Too many members, 40, 50 members in the exam, they will not ask. 40, 50 members means 3, 6, 9, 12, 27, 30, 47. Then 40 after counting say 23rd member, 23 into 3 means 9 and 69 after counting. Suppose you get doubt, then again from the 1, 2, 3, 4, 5, 6 you have to count. That much number of counting won't be there. 3 joints, 4 joints, that's all. Easily you can count by inspection itself. Such simple questions only they will ask you because their main intention is not to make you count up to 200. Main intention is have you understood the concepts or not. Okay, fundamentals if you are thorough only they will you can answer such questions. Okay. Now this is a question given for 2 marks. Considering the beam as axially rigid, degrees of freedom of the frame. Now I told you first we will calculate general case, whatever may be the problem. Tk when extensible. How many are possible? At a rigid joint in a frame, 3 are possible. But whereas roller support, it can translate, it can rotate. Y direction it cannot move. So at this point dk is 2. Here dk is 3. 2 means what? Delta Ax, theta A. Here what is 3? Delta Bx, delta By, theta B. Here also dk how much? 3. Here dk is 1. What is that 1 is? Theta d. Here delta Cx, delta Cy, theta C. Here delta Bx, delta By, theta B. So when extensible means here 2 plus 3 5 plus 3 8 plus 1 9 degrees. but he says axially rigid. So decay when inextensible. Decay when extensible minus number of independent displacements prevented. Number of independent displacements prevented. How many are prevented? There are 3 members, but he says only beam is axially rigid. That means what? All other members are not axially rigid. So number of independent displacements are only 1. Why only 1? Because only beam is axially rigid. In the exam, that much care should be there. Question we have to read thoroughly. Independent, either all members are rigid, all members are extensible, need not be there. Some only are axially rigid, some are not rigid. Then accordingly, we must be able to answer. So now, decay when extensible, when inextensible. General case is 9 degrees minus 1. You will get 8 degrees. But 4 options they have given like this. First option is, if you forget to read that axially rigid say, then 9 will be there. Then if you subtract 3, 9 minus 3 is 6, that 6 will be there. Then correct answer is 8. Then D 7 or 9, 7, 8, 6 will be there. Whatever mistake you make it, corresponding answer also will be there. So you should be careful. That's why it is a 2 marks question. They have given us 2 minutes time. Once now you understood how to make it, even such questions also you can complete in our stipulated time. Now let us see another question. Always remember that when bracing is done, bracing is 2 members. 2 members we should not subtract because 1 member is useless. 1 member is under compression, only 1 member. 1 member reduces the sway. That's all. Other members simply useless, whatever direction they move. We'll see what are the, I have repeated this point again with a numerical. Find decay. This is a hinge support. A roller support, and this is a guided roller support. Okay, this point say A, B, C. There is a hinge say internal hinge at D, E, F. So internal hinges at D, E, F. Now you see, once again I repeat the difference between guided roller, simply roller. Guided roller means this column is rigidly welded so that rotation is not possible. It will translate. That's all. Instead of rigidly welding, you put a bolt, say. That means to the rigid plate, again you weld two triangular plates, and to the two triangular plates make a hole, and this member is pinned. Because of that pin, it will rotate. Because of these rollers, it will translate. So translation, rotation are possible. It's simply roller support, but it cannot be lifted. Here there is a channel, here also channel. Channels will not permit the roller supports to be lifted up. It will always rest on the supports only. They cannot leave the support. Okay. So now this point now we'll take up. Simply we'll count, that's all. First general case, then inextensible case. At this point dk is 0. How much is dk here? Kinematic indeterminacy. For that you must know how it looks like. Dk at d. See, I will show here. Fixed. D here. There is one member here. This point is d. Okay. Now this, when you push it, wind load or something like that, it will sway. Due to compressive force, it will get compressed. So it can come here. D will come to d dash. This is d dash. That means two translations are possible. This is delta dx. This is delta dy. So d has come to d dash. Now there is a pin. These three members independently rotate. This member rotated by say theta 1 like this. This is say theta 1. This vertical member can rotate by another angle. Right? This member rotated by like this, say theta 2. This vertical member will rotate altogether by a different angle like this, theta 3. Theta 1, theta 2, theta 3 can be independent, and delta dx, delta dy. So dk at d is 5 degrees. What are the two translations? 3 rotations. Okay, like that. So here dk at d is 5. Here dk is 3. Here dk is 3. Dk is 3. Here dk is 4. Delta fx, delta fy. Theta 1, theta 2 for two members. Here dk is 3. Here dk is again 3. Here dk is 6. What are those 6? Delta ex, delta ey, and 4 independent rotations. Then here dk is 1. Here dk is 2. Because it will translate, it can rotate. But here it can only translate. Dk is only 1. Cannot be lifted, cannot rotate. Now you see dk when extensible. Count them 3, 6, 9, plus 4, 13, 16, 19, 25, 30, 34. 34 degrees. Now dk when inextensible. So general case, dk when extensible minus number of independent displacements prevented. Such structures where there is no bracing, all displacements are independent displacements. If you count the number of axially rigid members, so many you can subtract easily. That you can do when bracing is not done. all displacements are independent. That means no compatibility. Relations can elongate or contract independent of the other. Like this, when number of independent displacements prevented. See how many members are there? 1, 2, 3, 4, 5, 6 horizontal members, vertical members 8. So prevented are in this case is equal to number of axially rigid members. This you cannot use it when bracing is done because one member is useless. Under compression, bracing rod will not take any force, so it will not resist any displacement at all. Force itself will become 0 in that. So when bracing is done, don't use this formula, number of axially rigid members. Other cases we can do it. So total axially rigid members are 14. So you will get dk is equal to, general case is 34 degrees minus axially rigid members are 14. So you will get 20 degrees. Now what are those 14? Let us see what those 14 are. Note. In this case, vertical members are 8. 8 vertical members cannot come down. That means 8 vertical displacements are 0. In this case, 8 vertical displacements are 0. Next, horizontal displacements. See, the EF is over already. This point, let us say G, EF, G, H. This you take, say I, J, K. Joints we take it. Now loads are applied. Even if the members are inextensible, when wind load applies, it sways. Without elongating this member or contracting this member, electric pole is there, say. Without electric pole getting elongated or contracted, it can move. That's the first order displacement. So delta dx is there, say 5 mm. Then delta ex, gx, hx, all will be 5 mm only because these member elongations are 0. So whatever sway is there, all values are same. That means delta ex, gx, hx is known to us, but delta dx we don't know how much it will sway. One floor, one sway. Second floor, another sway, independent of the first floor sway. So delta Ix is independent of delta dx. If it moves by 2 mm, it can move by 5 mm also. But if it moves by 5 mm, at that floor level, all will move by 5 mm. Like that. Okay. So 6 horizontal displacements are known to us. Six horizontal displacements are not unknown displacements. That is, they are not independent displacements. What are they? If delta dx is known, then delta ex is equal to delta gx is equal to delta hx is equal to delta dx. If delta dx is known, these three values is also equal to delta dx. So these three are not unknowns. So 3 members, 3 displacement. Then next floor. In the next floor, if delta Ix is known, then we know delta Jx is equal to delta Kx is equal to delta Fx is equal to delta Ix, like that. So, 6 horizontal displacements are not 0, but we know them. But 8 vertical displacements are 0. So, total 14. That 14 you have to subtract. Instead of worrying which is equal, which is known, which is 0 and all, if bracing is not there, directly subtract number of axially rigid members. What that 14 you don't have to worry in the exam. Simply subtract number of axially rigid members because you are pressed for time. That much story is for your understanding out of examination hall. In the exam hall, how many rigid members are there? 14. So subtract 14, finish off in 10-15 seconds time. Okay. That means in this case, if delta dx is say 10 mm, if delta dx is equal to 10 mm, delta ex, delta gx, delta hx is also 10 mm. If delta ix is equal to say 20 mm, then delta ex, delta jx, delta kx, delta fx, these three also 20 mm. But this and these two are independent. One floor level sway, each floor can sway independent of the other floor. Now, next one. If you want to use number of axially rigid members also, if bracing is done, then only one member you have to count. Next, dk. Like this, they have given once a problem. Let us see how we should manage. First, we will take up general case. Now, you see, these members are there, this is like bracing. In this floor level, for one floor level, one bracing rod is enough, other will also, two directions sway, it will stop. So, 1, 2, 3, 4 bracing rods are there. Out of that, you have to count only 2. If at all it sways right side, okay, so this will be under tension, these two are useless. If it sways to the left side, then these are under tension, this will be useless. Okay, we assume that bracing rods are ineffective in resisting compression. So, accordingly, dk when extensible, dk when extensible. Count them. Here dk how much? 3. xy rotation. Here also dk is 3. dk is 3. Here dk is 3. Here there is a pin connection was there. So dk is How much you have to count? How many members are there, you see? 1, 2, 3, 4, 5, 6 members are there. One, two, three, four, five, six. 6 members are there. dk is 6. 6 members. See here, for dk when you are finding 1, 2, 3, 4, 5, 6. 6 members, 6 independent rotations. XY translations also we have to take. So dk will become 8. Next, here dk is 3. And here dk is 0. Here dk is only 3 rotations. And here dk is 0. Here 3 means 3 rotations. Here 6 rotations, 2 translations. So now, if you take count them 3, 6, 9, 9 plus 3, 12 plus 8, 20, 23, 26. So you will get dk when extensible 26 degrees. Dk when inextensible. Means dk when extensible minus number of independent displacements prevented. Number of independent displacements prevented. So how many you have to count is, see here, vertical members 1, 2, 3, 4, 5, 6. 6 vertical displacements are 0. Horizontal displacements you see 1, 2, 3, 4. 4 horizontal displacements. 4 horizontal displacements. Out of 4 horizontal displacements, 4 horizontal displacements, not unknown. Now you see, if the members are inextensible, it can also not sway. So sway is not possible, sway is not possible, sway is not possible. So you have to count now, since sway is also not possible, 6 horizontal displacements, 1, 2, 3, 4 horizontal displacements not unknown due to bracing. Sway is also not possible. So 6 horizontal displacements are 0. So 6 horizontal displacements are 0. 6 vertical displacements are 0. So number of independent displacements prevented are 12. So 26 minus 12, you will get 14 degrees. Now, instead of number of axial rigid members you want to count, say, how many are there? You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 members are there. If you want to write number of independent displacement prevented is equal to number of axially rigid members, then 14 you should not take, only 12 you have to take. Because if it sways to the right side, these are under tension, these are under compression, they are useless. So only 14 you have to count, 12 you have to count, but not 14. If it sways this side also, only these two are effective, these are useless. This is one way. This is completely we have analyzed. How many are there? 6. What they are also we have written. Now you see, I write now. We write in the next paper. Now you see, dk when inextensible is equal to dk when extensible minus number of, this is second, minus number of independent displacements prevented is nothing but number of axially rigid members. They are 12 but not 14. Why 14? Not 14. Because two bracing rods are useless or ineffective in resisting compression. That means we can write, it is assumed that bracing rods are subjected to tension only and reduce sway. They are ineffective in resisting compression. So, only difficulty you get is if bracing is done, how many axially rigid members you have to count, that will problem. If bracing is not there, no issue at all, number of axially rigid members you subtract. But if this type of inclined members are there, if this is inclined this way in the same direction, it will not be inclined. This rod, I can keep it here also into shape. That is called bracing rod, two bracing rods. Instead of providing bracing rod here, they have kept here. That's only difference. Here also same thing. This placket, keep it here. Only one is effective. Either here or here, but in the opposite direction must be there. If it is connected this way, this can be here or here, but in the opposite diagonals only should be connected. So if it sways one side, this is compression, say 0 force. So useless. Again, you should not count it as one sway is prevented. If it moves right side, if sway is stopped, say that sway is stopped because of this member only. This member will not stop any one more sway, because already this is stopping, this is useless. This is stopping, this is useless. So instead of 14, you should reduce 14, subtract 14, say. You should directly close this. 26 minus 14, number of independent displacements prevented. This is big story. Big story means brute way of solving the problem. 6 vertical displacements are 0. Then 4 horizontal displacements are not unknown. Due to bracing, another sway is also not possible. So each floor 2 another extra not possible. So total 6 are not possible. So 6 plus 6, 12. You see, thinking time will increase if you do this way. But if you remember that bracing means only one you have to count you in each floor level, then easily you can make it this way. Axially rigid members, how many if you are able to identify, then directly you can solve it. Means no great thinking will be required in the exam in 1 minute time. So how many displacements you are preventing, how many are known, how many are unknown, means the thinking process is so much. But this way you can finish off fast. Now you see that 14 earlier problem I gave you. If members are axially rigid, bracing is done, only rotations are possible. That way also you can count. How many rotations are possible? 1, 2, 3, 4. Here how many? 1, 2, 3, 4, 5, 6 rotations. 1. So number of rotations we will count, and I will tell you another way of doing the same problem. Third way. Because in the exam we don't know which idea you will get. Note. If members are axially rigid and bracing is done, only rotations are possible. Now you see dk. I change the color. Here dk is 0. Here only rotation is possible. It cannot sway, contract. So here one rotation because all members rotate by the same angle. So 1 here. Here only one rotation. All will rotate as a rigid body. Here only one. Here only one. Here also only one. But here pin connection is there. 6 independent rotations are possible. 1, 2, 3, 4, 5, 6 members. So 6 rotations. Inextensible case we are taking. Here 0. Here 3 independent rotations. 1, 2, 3 members. Here dk is 0. Here it is 0 anyhow. Now count them. You should get that. How much is that? Here we have, if you come back to this one, dk when extensible, how much you have calculated? Total value was, I'll repeat this one, 26. When extensible is 26 minus axially rigid members are 12. So you will get 14 degrees. Okay, that 14 you will get here also. See, count now. 1 plus 1, 2, 3, 4, 6 plus 4, 10, 10 plus 1, 11 plus 3, 14. 14 degrees means 14 rotations. Okay. If you remember this point, axially rigid, bracing is done in each floor. Then put only rotations, you count it, make it either this way or that way. Will give you this, even that count. Rotations also, here rotations we have to count. There in extensible case you have to calculate 26 and subtract how many axially rigid members are there. This will take say 1.5 minute time. This will take say 1 minute time. But this will take only 20 seconds time. Now, having understood this one, in the exam you decide which way we should proceed. Because after understanding everything, we don't know which idea quickly strikes. So patiently you have to sit down and recollect that concepts, then manage. Now one more question we'll see. Okay, now you see next question. Decay. Assume that in this case now we will take the inclined members. Like this are there A, B, C, D. Now in this case decay when extensible 6 degrees. What are those 6 degrees? Here is delta Bx, delta By, theta B. Here delta Cx, delta Cy, theta C. Now no bracing is done. So directly you can subtract number of axially rigid members decay when inextensible. Decay when extensible minus number of independent displacements, number of independent displacements prevented. Independent displacements prevented is equal to number of axially rigid members. Again, there are no bracing members. So axially rigid members are 3, directly we will take it because no bracing is there. So extensible is 6 minus 3. You can take it as 3 degrees. What are they? It can sway. So delta Bx, only one sway, one floor level, one sway. Then theta B, then theta C. So only these three, delta By, delta Cx, delta Cy, you can find from the uh, trigonometric relationship between the three members. Okay. So that if I see what is that relationship, we can get the value like this. How to get that? Now, when you are taking the first order displacements, I told you one cantilever beam, I applied vertical load, there is a vertical displacement, first order displacement. Horizontally also it will go in, that is B1, B2, that is delta By into theta B. That inward displacement is second order displacement because two displacements you have to multiply. All second order displacements you neglect. In the process, what happens when you neglected second order displacements, then the first order displacement delta Bx or whatever displacements we are calculating when members are axially rigid, all the displacements are assumed to happen perpendicular to the initial configuration of the structure because no inward displacement. So it displaces in the perpendicular direction of the original configuration. AB is like this. If its displacement is perpendicular to this configuration, that means it will come somewhere here. This is 90 degrees line. B has come to some B dash, let us say. CD is like this and it will go like this. C, let us say C1. This is say B1. To this 90 degrees, to this 90 degrees. And this deflection profile will go like this. Here initially horizontal was there. It is like this. Here also initially inclined member. This also horizontal member. These are the initial positions. Horizontal, inclined. Horizontal, inclined. Now how they rotate? Supposing that this rotates here theta b like this. Here also it rotates by some angle. Zoomed view we have drawn, that's all. Like this it rotated, say. Because I have drawn so high value, everybody should see. So it looks like a cable deflection. But actually CC1 is very small. So almost like that only will be there. But how to see that? For the sake of seeing the problem properly, compared to this and this, they are not drawn to scale. So I have drawn so much here. Now here if it is sagging, here also it must sag. This rotation, let us say theta b. Whatever value, this is sagging. Here also it must sag. Like this. Sagging, sagging. B1, this point, if I take this point, let us say B2. B2, this one. This I call it as a delta Bx. This angle with respect to vertical, this angle let us say theta. Then with respect to horizontal, this angle will be theta. Right? With respect to vertical, theta means draw a vertical line here also. And this angle is theta, 90 minus theta. Then it has to be theta. Like that. That is simple trigonometry. Theta, theta. This is 90 minus theta. So it has to be theta. So a line, if it makes with respect to vertical angle theta, a perpendicular line with respect to horizontal, it will make the same angle theta. Okay. Let us say this angle is say alpha. With respect to horizontal, this angle also will be alpha. This deflection profile for this one will go like this. This is hogging, so here also it should hog. Like this. Hogging is done. C has come to C1. If I drop a vertical line here, this is C1. This is a C2. If this angle is alpha, this has to be alpha. Now, from the trigonometric relationship, once if I know delta Bx or BB1, all other things I can find. Let us see what we can find here. Only one displacement. If delta Bx is known, we can find BB1. Then this vertical displacement you call it as a B1, B2 is a delta By. C2 is a delta Cx. This you call it as a delta Cy. We can find BB1, delta By, delta Cx, delta Cy. How to find? This angle is theta. So delta Bx is nothing but BB1 cos theta. So find BB1. Next BB2 is nothing but BB1 cos theta, B1 means what? This is B2 means what? Delta Bx. Find delta Bx. Next, B2 is also equal to CC2 is nothing but a delta Cx. So find delta Cx. Then C1. C1 means what? I can calculate. C2 is equal to C1 into cos alpha. So from this find C1. Now C1 C2. C1 C2 is nothing but delta Cy is nothing but C1 sin alpha. So find delta Cy. That means if I know delta Bx, I can find delta BB1. Delta Bx is already is known to us. BB2. Again we have written delta Bx is known. BB2 means, okay, delta, find delta Bx. B1, B2. Here we will make it as B1, B2. B1, B2 means, because that's already known to us, B1, B2 means BB1 sin theta. Same thing why we should write. You see here, BB1 sin theta. So find delta By. So BB1 delta By. Then delta Cx is same as BB2. Then C1 C2 means delta Cy is nothing but CC1 sin alpha. So independent displacement, if this is how we have taken, if delta Bx is known to us, delta By, delta Cx, delta Cy we can find. That in the end we can write. If delta Bx is known, we can find delta By, delta Cx, delta Cy. These three are not unknowns. Okay. This is only to understand which three displacements we have removed, which three displacements are existing. If I know these three, how to find the other one? Actually, in the moment distribution method, we require this one. If this displacement is delta, what is CC1 displacement? If BB1 is delta, what is CC1? A 2 marks question they can ask you. Only to find the relationship. BB1 if I know, how to find CC1? We can find from the symmetry, two triangles we have to draw. Quickly we can find CC1. All not necessary. BB1 means first find delta Bx. Okay. That means BB1 cos theta you take it, then delta Bx is known. Which means that delta Cx is also same. Right. So then CC2. We wanted CC1. So this is CC2 means what? Delta Cx. So delta Cx if I want, CC1 cos alpha is delta Cx. So delta Cx by cos alpha you will get CC1. How much it displaces? Like that. General expression I am not giving, you tend to by heart. Because I gave alpha here. But in the exam alpha they give with horizontal. Here theta I gave with respect to vertical, but they can give theta with respect to horizontal. So no question of by hearting. You must form a triangle B1, B2, C1, C2. Form a triangle, spend 1 full minute time at home. Now when you are practicing, then you change the angles from vertical to horizontal, then work out. Once if you work out in the exam, the speed of calculating the relative relationship between the displacements becomes simple. In case they ask you a question on the displacements, if this moves by delta, this moves by how much, like that, then you must understand that if the members are axially rigid, the all displacements are assumed to be acting perpendicular to the initial configuration of the members. First this member perpendicular to that one displacement, then this member perpendicular to that another displacement, then interconnect them. Then if it sags, it should sag. If it hogs, it should hog. One sagging, one hogging at a joint not possible if there is no external moment. That I told you in the moment distribution method. If one member sag, another member should also sag at a particular rigid joint if there is no external moment. Okay. Now, if you take now why that the second order displacements we have already I have given you already dk for floating shape. Now one more question we'll discuss. In the exam, two times they have asked dk for this structure 6, 5, 2, 1. Then 6 you have to answer. Another paper they asked 5, 4, 3, 2. Then you have to answer 3. Like that. In plastic analysis, we also get number of independent displacement modes. That means how many beam mechanisms, sway mechanism are there. Those types of mechanism are different from degrees of freedom. Kinematic indeterminacy is different from displacement mode. That displacement mode, if they give, is it a failure by beam mechanism or sway mechanism or combined mechanism? Like that, the displacement modes. Once you come to steel structures plastic analysis, there again I will tell you that kinematic indeterminacy is different. Number of independent displacement modes means sway mechanism, beam mechanisms are different. We will discuss that point again in the steel structures. Now you see dk for a floating ship. This is dk for a floating ship. We take it as 6 degrees. 3 rotations, 3 translations. Now you see, if you want to know what they are, top view of a ship I am showing. This is the top view of a ship, let us say. Okay, ship, it's moving right side. This is x-axis. Translation. In this direction, if this is a ship, let us say, top view I am showing, this is a ship. If it moves like this, that is called surging. And about this axis, if it rotates like this, that is called rolling. Okay. Next, in the y direction, this one can move up and down also. That is called heave. Up and down displacement is called heave. Then laterally also it can move. This is called sway. 3 translation means surge, sway, heave. Rotations. In the surge direction, if this is called rolling, fluid mechanics it will come. This is called rolling. About this transverse axis, if it moves like this, it is pitching. Rolling is like this, pitching is like this. If it rotates like this, about the z axis, this about z axis if it rotates, we call it as yawing. So this is x axis. I give you all the things, motions. X direction, if it translates, this is called surge. About this axis, if it rotates, x-axis rotates like this. This is called rolling. That means that this way I can show like this. That will be call it as rolling. This is x-axis, you take it. Such about that axis, if it rotates, rolling. Then y direction. This is the y direction, let us say, up and down. This translation, up and y direction, if it moves, this is called heave. If it rotates about this one, like this is called yawing. That means it rotates either this way I can show, double arrow I can show, yawing. Sidewards if it moves, z direction, this you take as z axis. If it moves sidewards, that we call it as sway. If it rotates about this axis, like this is called pitching. That means about z axis if it rotates. So now you understood like this. This is a ship, let us say, floating in air, floating in water. Move forward, surging. About that axis it rotates, that is called rolling. If it moves sidewards, it is called sway. About this axis rotation means like this. Okay, this is called pitching. Then above also it can move. Leaving the water, it cannot jump, go out. That is called heave. About that axis, if it rotates like this is called yawing. So, three translations, three rotations are possible. So, three rotations are this one: rolling, pitching, yawing. Three translations: surge, heave, sway. Okay. So, six independent displacements. If we take a railway engine or train movement, then independent displacements you have to take it as only one. dk for a locomotive is only 1 degree. Why only 1 degree? Trains also they rotate. Suppose this is the train, let us say, it's moving like this, forward, backward, one motion. If at all it rotates like this, that curvilinear motion is fixed rotation. You know the radius, you know the theta, that at what location it is there, it's fixed quantity, it is not independent because radius and theta of the track is fixed. Okay, so you cannot count that as an independent rotation. Now this train is moving like this, there is a wobbling effect. We don't want wobbling at all. Wobbling should not be there. If it happens, that is happening, that's all, but that is not a degree of freedom. But railway track is there, slightly it will move, that's all. But if it moves railway track, if it leaves the railway track and moves like this, say, that is also possible displacement only. But that is not called displacement, that is called accident. Leaving the railway track movement means all types of accidents are not independent displacements we should consider. Okay, so we have to assume that no accidents took place. It is moving on the railway track. It can move forward, backward, only one displacement, independent displacement. Curvilinear motion it can take up, but radius and theta is fixed quantity, so that they are not unknowns. Then upward and downward it cannot move. Leaving the railway track it cannot go up. Moving up means accident happened. Leaving the railway track it moves horizontally, also accident only. That is not independent displacement. So dk for a locomotive we have to consider only one. Now take one more question. Find ds and dk. Assume that we have a structure like this fixed here. Bin then it was something like this. Okay. It comes like this, say. Here assume that we have a guided roller support. This is the problem. Let us name them. This point, let us say A, B, C, D, E, F. When you are calculating ds or dk, d kinematic indeterminacy, this also you have to consider it as a joint. Free end is a joint. We should not think that accidentally he extended the line. Let us ignore. We should not think that way, because once a line is shown, however small it is, if it extended beyond, that is like a cantilever. He is expecting you to check whether you will treat this as a joint or not. So you have to treat this as also a joint, FG. Say a curved member meeting a straight member somewhere here, FG. This you take say H, I, J, K. Like this I have given. This only to tell you the complete structural behavior. That's all. Now, when you want to find ds, 3 into number of cuts minus number of reactions unnecessarily added to make stable cantilevers. Okay, this is not there. To make stable cantilevers. Now you see, at B, how many cuts are required? You see, 1, 2. This cantilever is separate. 3, 4. This is center when it comes out, separate. That's all. Number of cuts are 4. 3 supports, so 3 cantilevers. So 3 cantilevers. Okay, number of cuts are 4. Next, here B, there is a hinge support. It's supposed to be fixed one. Hinge means one fixed moment reaction is missing, so -1. Here translates, so you fix it. Unnecessarily you are fixing by adding one horizontal reaction, so much you subtract. So you will get 3 into number of cuts are 4, -1 at B, -1 at C. So 12 minus 2, 10 degrees. Okay. Next, dk. Dk when extensible. Dk, I will use the black one. Here dk how much? 0. Here dk is 3. Here this also you have to consider it as a joint. Dk is equal to 3. It is treated as a joint. So anyhow this you will take it. Dk is 3. Here J is a joint, so dk is 3. K, dk is 3. G you have to take it as a joint. Dk is 3. 3 at G this is. This is dk at 3. This is at F. This is dk is 3. This here dk is 1. Here dk is 1. Now count them. 0, 3 plus 3, 6 here. 6 plus 1, 7 plus 3, 10 plus 3, 13. 13 plus 3, 16. 16 plus 3, 19. 19 plus 3, 22. 23 plus 3, 26. So 26 degrees. See, no bracing is done. So when inextensible, when you take number of axially rigid members, directly subtract. So dk when inextensible, dk when extensible minus number of independent displacements prevented. Independent displacements prevented is nothing but number of axially rigid members. Number of axially rigid members. How many axially rigid members are there? Vertical members you see 1, 2, 3, 4, 5, 6. Horizontal members 7, 8, 9, 10, 11, 12. So 12 axially rigid members are there. Entire curved member is one member you will take. Overhang you have to take one member. So 26 minus 12 is equal to 14 degrees. Now if you want to see what those 14 degrees are, or how many 12 you have removed is, see here. In this case, 6 vertical members are there. We want to know now what those 12. 6 vertical members. So 6 vertical displacements are 0. Then at this floor level, 3 horizontal displacements are not unknowns. That means what? If delta dx is equal to 10 mm, supposing that, now delta ex, delta fx, delta gx is also 10 mm. Okay. So 3 are gone here. 6 vertical displacements are 0. 6 plus 3, 9. Next, if delta hx is equal to say 20 mm, delta ix will be 20 mm only, not unknown. Okay. Next, if delta ix and delta kx are known, we can find delta jx and delta jy. So delta jx and delta jy are not unknowns. From simple geometry, if this displacement is known, this is known, say, members are inextensible. This is a 5 mm, this is a 3 mm. Then j, how much it moves? 5 minus 3 is 2 mm. We can make it directly. So similarly, the triangles we can form, as I told you earlier, inclined members, trigonometric relationship I have obtained. So if I know how much this moved, how much this moved, I can predict how much this moved horizontally, how much this moved vertically. We can find them. They are known quantities, but rotation is independent, theta j. So how many are missed? 6 vertical, 3 horizontal, 9. This is 10, 11, 12. So it's like this. Finally, 6 vertical members, 6 vertical displacements. 6 vertical displacements are 0. Then 3 plus 1, 4 horizontal, 4 horizontal displacements are known. Then 4 only. Here 3, 4, 5. This is 5 horizontal displacements are known to us. Then 6 plus 5, 11. Then what else is left out? Delta Hx is known. Delta Ix is also known. This is 6. This is 3. Here 4, 5. One vertical displacement, that means 6 is not that, 7. Total 7 vertical displacements are 0. 5 horizontal displacements are known. 7 plus 5, 12. Like that. What they are, now I have explained. In the exam, this is not required. This is only for our understanding what the things happened. 12 you subtracted. What exactly those 12? If at all you wanted to know, this is the 12. But in the exam, let me see what those 12 are. You should not take it. It will waste at least 1 minute time. Simply this one. What is decay when extensible case? How many axially rigid members are there? Directly subtract. If you have a curved member, take it as a one member only. Okay. So then if you have a small piece overhang, however small it may be, that you have to treat it as a joint. G is a joint. Free end is treated as a joint. This one. Free end is taken as a joint. I told you why you have to take it. Wherever cross section changes, configuration changes, or if material changes, it is treated as a joint, like that. Okay. Now we'll see after this stability of structure.